In the latter half of the 20th century, physicists encountered a tantalizing conundrum. The two most successful frameworks that describe the universe, quantum mechanics and general relativity, seemed irreconcilable. A revolution in thought was brewing, one that required a radical reshaping of the most fundamental concepts underlying reality. Enter string theory, a bold and ambitious attempt to reconcile these two pillars of modern physics by proposing a profound yet simple alteration to the nature of the universe's most basic constituents. String theory posits that the subatomic particles traditionally thought to be point-like dots with no structure are in fact tiny, one-dimensional strings. These strings vibrate at various frequencies, much like the strings on a musical instrument. It is this vibrational state that dictates the properties of particles: mass, charge, spin, thus unifying them under a single theoretical umbrella. This is not merely a cosmetic change. It is a profound insight that promises to be the key to unlocking the secrets of the cosmos. The historical trajectory of string theory is a testament to the persistence and creativity of the theoretical physics community. Initially developed to explain the strong nuclear force, the force that binds quarks together in protons and neutrons, string theory was temporarily set aside with the rise of quantum chromodynamics. However, it was soon realized that string theory's very shortcomings in describing nuclear physics were strengths when it came to the puzzle of quantum gravity. The theory's evolution was marked by the recognition that one of the vibrational states of the string corresponds to the graviton, the theoretical particle that mediates gravitational force. As the theory developed, it branched out, leading to the formulation of different versions. The earliest version, bosonic string theory, included only bosons, leaving out fermions, which are essential for a complete particle theory. This led to the development of superstring theory, which incorporated fermions and introduced a new symmetry called supersymmetry, relating bosons and fermions. 5 consistent versions of superstring theory were proposed, and the quest to understand their interrelations paved the way for M-theory, a more profound conceptual framework believed to encompass all string theories in a higher dimensional reality. String theory's mathematical elegance has not come without controversy, however. One of the most significant challenges has been its prediction of an enormous landscape of possible universes, a multiverse, each with its own set of physical laws. Critics argue that the theory's immense flexibility makes it difficult to produce testable predictions, thus questioning its empirical verifiability. Furthermore, string theory's reliance on extra spatial dimensions, beyond the familiar 3, poses both an explanatory challenge and an opportunity. These additional dimensions are compactified, curled up in configurations so small as to be invisible to current experimental techniques, leading to a rich interplay between theoretical predictions and the geometry of these hidden dimensions. Despite these challenges, string theory has made significant contributions to mathematical physics, providing fresh insights into black hole physics, cosmology, and the very structure of space and time. It has also elucidated connections between seemingly disparate concepts in physics, such as the anti-de Sitter conformal field theory correspondence, ASCFT, which proposes a startling duality between gravity in a negatively curved spacetime and a quantum field theory without gravity. As physicists strive to develop a complete and consistent picture of string theory that accurately reflects our universe, the theory remains a profound and tantalizing glimpse into the potential unity of all physical laws, a theory of everything that could one day explain the fabric of the cosmos in its entirety. Whether string theory will ultimately succeed in this ambitious goal remains one of the most profound and compelling questions in modern theoretical physics. String theory's mathematical sophistication extends far beyond the remit of a physical framework. It has enriched the realm of mathematical physics, providing tools and concepts that have led to novel insights across various domains. The interplay between string theory and mathematics is a story of unexpected cross-pollination, where the pursuit of a unified physical theory has yielded a trove of mathematical treasures. The contributions of string theory to black hole physics are profound. The theory has reframed the understanding of black holes, offering a microscopic explanation for their thermodynamics and entropy, a problem that had long puzzled physicists. By treating black holes as solutions in string theory, complete with a horizon of strings and branes, physicists have been able to derive the entropy of certain black holes, finding remarkable agreement with the predictions of classical general relativity. This has illuminated the quantum nature of black holes, providing a clearer picture of how these enigmatic objects comply with the laws of quantum mechanics. Cosmology, too, has benefited from string theory's rich mathematical structure. The theory's mechanisms suggest explanations for the early universe's inflationary phase, tackling questions about the Big Bang and the universe's subsequent evolution. String theory has brought forward the concept of a landscape of possible universes within a grander multiverse, where the constants and laws of physics vary from one universe to another. Although the idea of a multiverse is controversial and difficult to test, it has spurred new ways of thinking about the cosmological constant problem and the fine-tuning apparent in the physical laws that govern our universe. In condensed matter physics, string theory has made unexpected connections that have advanced the field. The ADS-CFT correspondence, a jewel in the crown of string theory, proposes a powerful duality between a type of string theory in anti-de Sitter space and a conformal field theory in one fewer dimension. This correspondence has provided a new perspective on the behavior of strongly coupled quantum systems, which are notoriously difficult to analyze by conventional means. It has found applications in understanding phenomena such as the quark-gluon plasma and high-temperature superconductors, offering a novel framework for exploring the properties of these complex systems. Moreover, string theory has been instrumental in discovering new dualities within physics, which are equivalences that relate seemingly disparate theories. These dualities have profound implications, suggesting that different theories may be simply different limits or manifestations of a single underlying theory. This has led to a deeper understanding of the symmetries and invariances at the heart of physical laws, and has prompted a search for a unified mathematical description of all fundamental forces and matter. The relationship between string theory and pure mathematics is symbiotic. The theory has led to the development of new mathematical techniques and the discovery of previously unknown relationships within mathematics itself. For example, string theory has stimulated the development of new algebraic structures and geometric constructions, deepening the understanding of Calabi-Yau manifolds and their role in compactification, which is essential for relating higher dimensional string theory to the observable four-dimensional world. In summary, string theory has expanded the boundaries of both physics and mathematics, establishing itself as a central paradigm in the quest for a deeper understanding of the universe. Its mathematical underpinnings have proven to be as rich and surprising as the physical phenomena it aims to explain, offering a glimpse into the intricate tapestry that is the mathematical universe. One of the most radical yet essential aspects of string theory is its reliance on extraspatial dimensions. Beyond the familiar three dimensions of space and the singular dimension of time that form the four-dimensional spacetime of Einstein's relativity, string theory requires additional spatial dimensions for mathematical consistency. The necessity for these extra dimensions arises from the intricate vibrational patterns of strings, which demand a higher dimensional arena to fully express their physical potential. The mathematical consistency of string theory hinges on these extra dimensions. In its various incarnations, string theory requires a spacetime of 10, 11, or even more dimensions. Yet, the world as it is observed appears to have just 4 spacetime dimensions. This apparent discrepancy is reconciled through a process known as compactification, wherein the surplus dimensions are folded up into complex minuscule shapes so small that they elude detection by current experimental means. Compactification is not merely a theoretical sleight of hand. It has profound implications for the physical properties of the universe. The specific way in which these additional dimensions are compactified determines the types of particles and forces that manifest in the lower dimensional, observable universe. The shape and size of the compact extra dimensions dictate the masses of particles, the strength of forces, and the properties that govern the interactions of elementary particles. Thus, Compactification has the potential to explain why the universe has the particular physical characteristics it does, out of the vast landscape of possibilities allowed by string theory. Delving further into the complexities introduced by these extra dimensions leads to the concept of brane-world scenarios. In this framework, our familiar four-dimensional universe is envisioned as a brane, a membrane-like object of higher dimensions, floating within a higher dimensional space. This perspective revolutionizes the conventional understanding of gravity and its weakness compared to the other fundamental forces. Gravity, as postulated in brane-world scenarios, is fundamentally a higher dimensional force that appears weak in the four-dimensional brane because it propagates through the full extent of the higher dimensional space. These brane-world scenarios provide an innovative context for addressing some of the most perplexing questions in cosmology and particle physics. They offer a new vantage point to tackle the hierarchy problem, the question of why gravity is so much weaker than the other fundamental forces. Moreover, they suggest that phenomena such as dark matter and the behavior of galaxies could be influenced by the gravitational effects of extra-dimensional spaces and the physics of branes. The introduction of extra dimensions in string theory challenges the traditional notions of how space and time are woven into the fabric of the cosmos. It suggests a universe far more complex and multidimensional than ever before imagined. Yet, this complexity is a necessary ingredient in the quest for a singular, unifying theory that can fully reconcile the quantum world with the cosmos on the grandest scales. A theory that not only describes, but also explains the profound mysteries of the universe. The quest for a unified theory, one that coherently melds the quantum realm with cosmic expanses, remains one of the most ambitious and challenging endeavors in theoretical physics. String theory has long stood at the forefront of this quest, offering a framework that holds the promise of a unified description of all fundamental forces and forms of matter. Yet, despite its mathematical allure and theoretical potential, string theory faces significant challenges that must be overcome to fulfill its promise as a theory of everything. One of the central pursuits within string theory is to find a specific solution, a particular configuration of the theory's many parameters, that accurately mirrors the universe as it is observed. This includes matching the observed spectrum of elementary particles, encapsulating their masses, charges, and other quantum properties, as well as accounting for the enigmatic cosmological constant, the value of which drives the accelerated expansion of the universe. A key obstacle is the lack of a non-perturbative definition of string theory. The theory's predictions are largely based on perturbative techniques, where interactions are treated as small deviations from a free theory. However, many phenomena of interest, such as the behavior of spacetime at the Planck scale or the properties of black holes, are inherently non-perturbative. They require an understanding of string theory beyond the limits of perturbation in regimes where interactions are not weak and the fabric of spacetime itself may be fundamentally altered. Compounding the complexity is the vast landscape of possible universes predicted by string theory. With a multitude of ways to compactify extra dimensions and a staggering array of vacuum states, string theory appears to allow for an almost infinite variety of universes, each with its own set of physical laws. This multitude of possibilities presents a profound challenge: how to extract predictions that are testable in our particular universe. Critics argue that this multiplicity makes it difficult to make concrete predictions, which is a cornerstone of empirical science. Despite these challenges, efforts to understand the non-perturbative aspects of string theory have led to profound insights. The discovery of dualities, which reveal deep connections between seemingly disparate physical systems, has provided ways to relate strong coupling phenomena in one theory to weak coupling phenomena in a dual theory. This has offered glimpses into the non-perturbative regime, hinting at the unity lying beneath the surface complexity. Furthermore, string theorists have made significant progress by exploring the properties of the theory in lower dimensional settings, where calculations are more tractable. These toy models have provided valuable intuition about higher dimensional string theory and have sometimes led to surprising discoveries that apply to our four-dimensional world. The quest for a unified theory is not just a technical endeavor, it is a philosophical and conceptual journey. It forces physicists to grapple with the fundamental nature of reality and to question the principles that underlie the universe. String theory, with its rich mathematical structure and bold revisions to conventional physics, continues to be a leading candidate for a final theory. Its development is a testament to the human desire to understand the cosmos at the deepest possible level, to uncover the principles that govern everything from the smallest particles to the largest cosmic structures. As the search for a unified theory continues, string theory remains at the forefront, a beacon of possibility in the uncharted waters of fundamental physics. It is a quest that transcends generations, a collective human endeavor that seeks to reveal the most profound truths about the nature of existence.